In the world of medical AI, omics data, genomics, transcriptomics, proteomics, holds the key to unlocking disease mechanisms, discovering biomarkers, and personalizing treatments. But this data is deeply sensitive. Every gene expression profile, every tissue scan, carries intimate information about an individual's health, genetics, and even predispositions. Sharing such data across institutions is fraught with privacy risks. That's where federated learning steps in. Instead of pooling raw data in a central server, FL lets multiple institutions train a shared model locally, only exchanging model updates. It's a powerful idea, collaboration without compromise. But FL alone isn't enough. Malicious actors can still reverse engineer training data from gradients using attacks like model inversion or membership inference. Even a single gradient can leak private information. So researchers turn to two leading privacy-preserving techniques: differential privacy and homomorphic encryption. DP adds calibrated noise to gradients, mathematically guaranteeing that no individual's data can be distinguished. The smaller the privacy budget, the stronger the protection. But here's the catch: stronger privacy means more noise, which degrades model accuracy. It's a fundamental trade-off. On the other hand, he allows computations on encrypted data. Clients encrypt their gradients before sending them. The server can aggregate these ciphertexts directly, summing them up without ever decrypting individual contributions. No noise, no accuracy loss. But he comes at a steep cost. Encryption, decryption, and ciphertext operations are computationally expensive. Running it on every client can slow down training dramatically, especially on devices with limited resources. So we face a dilemma. DP is lightweight but noisy, he is accurate but heavy. Neither solution works perfectly in real-world federated settings, where clients vary widely in hardware, bandwidth, and privacy needs. Enter PPML-Hybrid, a smart, adaptive framework that combines the best of both worlds. In PPML-Hybrid, each client autonomously chooses its privacy mode based on its own computational capacity and privacy requirements. No central rule forcing everyone into one method. Clients with strong hardware, like hospitals managing genomic data, can opt for he to send noise-free encrypted gradients. Clients with weaker devices, say clinics with older laptops or mobile units, use DP for lightweight protection. This creates a dynamic hybrid system. Some clients contribute clean, accurate updates via he, others contribute noisy but efficient updates via DP. The server then aggregates each group separately, decrypting the HE group's summing the DP group's noisy gradients, and combines them into a single global model update. The result? A system that balances privacy, utility, and efficiency in real time. We tested this on a real-world spatial transcriptomics dataset of human breast cancer, 23 patients, 68 tissue sections, over 30,000 spatial spots. Each spot has a histology image patch and gene expression data. Our goal: predict gene expression from tissue morphology, a critical task for tumor subtyping and biomarker discovery. We compared PPML-Hybrid against two baselines: PPML-Omics, a DP-only method that uses local DP and decentralized shuffling, and HE-only, which uses full homomorphic encryption with no noise. The results were striking. First, model accuracy. The HE-only method achieved the lowest MSE because it adds no noise. But PPML-Hybrid came remarkably close. With just 50% of clients using HE, it matched HE-only performance at tighter privacy budgets, while outperforming PPML-Omics by a wide margin. Even with only 20% HE clients, it significantly reduced error compared to DP-only. Why? Because the noise from DP clients is effectively averaged out by the noise-free contributions from HE clients. The hybrid aggregation acts like a filter, suppressing the impact of noisy updates through the stability of clean ones. Second, computation time. He only was the slowest. Encryption and decryption are costly. PPML-Omics was the fastest, as DP adds minimal overhead. But PPML-Hybrid, it sits in the sweet spot, significantly faster than he-only, while still achieving near-optimal accuracy. And as the proportion of HE clients increases, computation time rises, but only linearly. Crucially, because clients choose their mode based on their own resources, the system avoids overloading weak devices. This isn't just theoretical. In practice, PPML-Hybrid enables heterogeneous environments, a mix of high-end research labs, small clinics, and mobile units, to participate on equal footing. High-resource clients contribute high-fidelity updates. Low-resource ones contribute safely and efficiently. The model learns better, faster, and more securely. We also explore the trade-off between HE ratio and performance. Increasing the fraction of he clients improves accuracy, but at the cost of longer training rounds. But with intelligent client selection, we can tune this balance. For example, in early training rounds, you might use more he clients to build a strong foundation. Later, shift toward DP to reduce overhead. This flexibility is key. Privacy isn't one-size-fits-all. A research institution may demand maximum confidentiality and choose he. A community clinic may prioritize speed and accept DP. PPML-Hybrid respects those choices, while still delivering a robust, accurate model. And the implications go beyond Omics. This hybrid framework can be applied to any federated learning scenario, where privacy, accuracy, and efficiency must be balanced. Medical imaging, financial modeling, smart cities. The core idea, letting clients choose their own privacy mode, can scale to thousands of heterogeneous participants. Of course, challenges remain. Future work will explore more sophisticated client selection policies, considering not just compute power but also network latency, threat models, and even adversarial behavior. We'll also investigate multi-key HE to prevent collusion between server and any single client. But for now, PPML-Hybrid proves a vital point. Privacy and performance don't have to be enemies. With smart design, we can build systems that are not only secure but also practical, scalable, and accurate. In the race to unlock the secrets of human biology with AI, we can't afford to sacrifice privacy. But we also can't afford to sacrifice performance. PPML-Hybrid shows a path forward, one where collaboration doesn't come at the cost of trust. Because in the future of medical AI, the most powerful models won't be built on data silos. They'll be built on shared intelligence, protected by adaptive privacy, and trained in real-world conditions. And that's the future we're building.